This lesson is on istables, which is part of HL equilibrium if you're taking IB chemistry. Here's an example of an istable. Here we are looking at a reaction that is at equilibrium. So HA is going to H plus and A minus. This, by the way, is the dissociation of a general acid according to Arrhenius. That's not something that we need to worry about here right now. The fact is that this reaction has reached equilibrium. So istable, ICE, is an acronym that stands for initial concentration, change in concentration, and then equilibrium concentration. The reason we call this a table is because typically we draw it in the form of a table. In these types of questions, a lot of times you'll be given the initial concentration of this reactant here. In this case, my reactant is HA, and the concentration is 0.150. M here stands for molarity. If you're an IB, this is moles per dm cubed. So typically, you'll be given the initial concentration, and then you'll be asked to do some stuff. And you'll see one of the things that they will ask you is they will ask you to find Kc, or they will ask you to find the equilibrium concentrations of all the reactants. So when we're setting up our istable, we put the initial concentration. If you're only given the concentration of the reactant, you just put the initial concentration of the reactant. The products have not been made yet, so their concentration is going to be 0. The important thing is this change line. It's negative for a reactant, and it is positive for a product. Why do we put X? Well, because the change is basically saying, look, here is my initial concentration. What's going to happen is the concentration of this reactant is going to go down as the forward reaction happens, and these concentrations will go up. By how much? I don't know. That is the whole point of setting up an istable. When you start to do questions like this, you will see the importance of istables and why we need to set them up. So here, what I'm saying is that my concentration of my reactant is going to go down by X amount. I don't know how much that is. We're going to find out what X is. But the negative is significant here because the negative is telling me that it's going down, and the positive here is obviously telling me that it is going up. Now, the other important part of this, and one of the most important parts, will be the equilibrium line or equilibrium concentration. And here I'm saying that at equilibrium, I'm going to have 0.15 moles per liter of this minus X. Why? Because that was my initial concentration. This is how much of it was reacted, and this is how much I have at equilibrium. Now, how much H plus do I have at equilibrium? Well, at equilibrium, I had 0 to begin with. Now I made X amount, so I have X amount. And here, my A minus, I had 0 at the beginning. Now I have X amount, so I have X amount. Now, let's take a look at some different types of questions that you'll be asked here. So, once again, when you're setting this up, this line right here, make sure that it follows the stoichiometry of that original equation. If I had a 2 here, this would be negative 2x. Okay? Likewise, if I had a 2 here, this would be positive 2x. All right, there's 3 specific types of problems that I've outlined here. Number 1, you could be given the initial concentration of the reactants and the equilibrium concentration of one of the species. What I mean by species is reactant or product, and you can be asked to determine the equilibrium concentration of the reactant of the remaining species and to find the equilibrium constant. Well, let's take a look at a question and then we'll come back to this. So in this reaction here, we have N2 plus 3H2 going to equilibrium, so 2NH3. You have 1.5 moles of N2 and 3.5 moles of H2. They're both added to 1 liter at 700 degrees Celsius. As a result of the reaction, the equilibrium concentration of NH3 became this much. What is the value of the equilibrium constant for this reaction? So if I'm solving this question here, I'm going to leave the states out for now. This is my reaction here. By the way, some people call this the ristable. They call this the reaction and then do the istable. So here is my istable. So if I'm setting up my istable here, you notice that I have 1.5 moles of N2 in a 1 liter container. Now, you can put moles inside here, but remember that at some point towards the end, you have to convert the moles to concentration. My suggestion to you is to convert these moles to concentration right away. Now, in this case, because I'm dividing by 1 liter, remember, concentration is moles divided by volume in liter. Because I'm dividing by 1 liter, my moles and concentration are the same. So it's 1.5 moles of nitrogen, and I have 3.5 moles of hydrogen, and then I have 0 ammonia. Why? Because this is the initial concentrations. Now, what's going to happen here is my change line here, these are my reactants, so these are going to go down in value by how much? Well, this is going to go down by negative X. This is going to go down by negative 3X. Why? Well, we learned this in kinetics. Those mole coefficients there So basically, what I'm saying is, if this is going down, or it's being consumed at a rate of 1 mole per liter per second, this guy is being consumed at a rate that's 3 times faster. So that's why we put a negative 3x here, and this is going up by 2x. And then at equilibrium, I have 1.5 minus x of this. I have 3.5 minus 3x of this. And then I have 0 plus 2x, or just 2x of that. It's very important for you to learn how to set this ice table. Now, this question is pretty easy. This is the first one. They're saying that the equilibrium concentration of ammonia is 0.54 moles per liter. So what they've essentially given you is this. They've given you the value of the 2x, which is 0.540. Now, that's very handy because that makes your life a lot easier. Now, they've asked you to find Kc. So Kc, in order for you to find Kc, remember Kc, which is the equilibrium constant, is the concentration of NH3 squared, right? This is how we write the expression, divided by concentration of N2 times the concentration of H2 cubed. So these concentrations are equilibrium concentrations, which means I need the value of N2 at equilibrium, and I need the value or the concentration of H2 at equilibrium. So what I'm going to do here is I'm going to take what's given to me in the question, which is this value right here. 2x is equal to that. I am going to solve this because the 2x equals 0.540. I'm going to find the value of x, and I'm not going to do that for you guys. You guys can do this on your own. Once I find the value of x is going to be some number here. Once I find that, I'm going to take this x value here, and I'm going to plug it into this. I'm going to plug it into that, and I'm going to find the concentration of my nitrogen at equilibrium. I'm going to find the concentration of my hydrogen at equilibrium, and what I'm going to do now is I'm going to take those numbers. I'm going to take the value that I found here, the value that I found here, and the value they've given me here, and I'm going to plug those numbers in here, and I'm going to find the value of my Kc. This I would consider an easy question. Anytime you're given the equilibrium concentration of either the reactants or products, this question tends to be easier. The second type of question here is if you're given the initial concentration of the reactants and Kc, and you're asked to find the equilibrium concentration of all reactants and products. This can be a little bit more difficult in the sense that it will involve a little bit of math. However, there's two types of problems that we can categorize here. Number one, we can run into a question that's like perfect squares. I'll show you an example of that. And then we have another one where here you might run into a quadratic. So here we have a little bit of a loophole. If your Kc value is very small, if it's 1 times 10 to the negative 4 or smaller, we can ignore the change in the concentration of the reactant. And you will see that this will avoid a quadratic. Let's take a look at an example here. It says here, in a 10-liter flask at 500 Kelvin is filled with 0.3 mole of hydrogen and 0.3 mole of iodine. What are the equilibrium concentrations of all three gases? So here is my equation here. Once again, I am going to set up my ice table here. So notice here, they did not give me the equilibrium concentration of reactants or products like they did in the last question. They did give you the Kc though. They said the Kc is 45. So here's what they're saying. They give you the initial concentration of these guys. So once again, here you're going to have to divide. So you have mole and mole, and this time it is in a 10-liter container, which means you are going to have to do this on your own. So 0.3 divided by 10, you have to convert that into concentration. 0.3 divided by 10, those are my initial concentration. The initial concentration of this is going to be 0. So when we are looking at this here, what's going to happen, my change line here is going to be negative x for this, and it is going to be negative x for I2, and it's going to be positive 2x for my HI. Once again, it follows the stoichiometry of your equation. How much do I have at equilibrium? Well, when you solve this, you get 0.03, and this is also 0.03. At equilibrium, I have 0.03 minus x, 0.03 minus x, and then I have 2x. So what they're asking you for now is to find the equilibrium concentrations of all three of these. Now remember, my last question, I was given the value of the equilibrium concentration of this guy. In this case, I'm not. So this, like I said, involves a little bit of work. So we're going to write the expression for this. Kc equals HI squared, concentration of HI squared divided by the concentration of H2 times the concentration of I2. So I'm given the Kc, which is 45. So now in here, what I'm going to do is I'm going to plug in my equilibrium concentrations. My equilibrium concentration of HHI is going to be 2x squared. My equilibrium concentration of these guys is just going to be 0.03 minus x. And because I have two of them, I'm just going to square this. Now, anytime you have two squares on top of each other like this in the numerator and denominator, we call this a perfect squares problem. What you are going to do now is you're going to take the square root of this side and you're going to take the square root of your 45. So what you end up with is square root of 45 equals square root of 2x squared over 0.03 minus x squared. So if you don't know how to solve this, basically this side becomes 2x over 0.03 minus x, and this is just going to be square root of 45. Now, I don't have a calculator with me right now, but this is obviously a lot easier to solve than this, right? If you had the original equation. So here, basically the way you would solve this is this would cross multiply into that. The square root of 45 would multiply into 0.03 minus x, and that will all equal 2x. Now, you'd have to solve this, find the square root of that, and then you can isolate for x. Now, once you find the value of x, you are going to take that value of x and you're going to plug it in here, you're going to plug it in there, and then you're going to plug it in there. So remember, the question here asks you, what are the equilibrium concentrations of all three gases? So my equilibrium concentration of all three gases here, well, I was missing the value of x. Once I find the value of x, I am good to go. Now, this question here could run you into a quadratic, and you have to be careful. So one way to get away from a quadratic, now if you're an IB, you will not get a quadratic, but one way to get away from a quadratic is we take a look at the value of the Kc. If your Kc is really small, let's say if the Kc was 1 times 10 to the negative 6, what does that tell me? That means that equilibrium lies to the left, right? Remember, Kc is products divided by reactants. So if my Kc is really small, that means that I have a lot of reactants left over. Essentially, if your Kc is 1 times 10 to the negative 4 and smaller, I can actually say, look, the equilibrium concentration of my reactant is essentially the same as my initial concentration, which means that I can ignore my change. Now, you must state that assumption. That is an assumption, but do that if your Kc value is 1 times 10 to the negative 4 and smaller. Now, if you do that, you would avoid a quadratic. The last type of question here is this last one here. And here is one where you're given the initial concentration of all species and the value of Kc, and they were asking you to find the equilibrium concentrations of all species. So this will definitely look very different. So let's take a look at an example here. So here we have HSO4 minus, we have H2O liquid. Remember, liquids and solids are left out of the equilibrium expression because their concentrations remain constant. What they've done here is that they gave you the concentration of HSO4. These are the initial concentration. So they give you the concentration of this. They give you the concentration of H3O plus, and they give you a concentration of SO4 2 minus. So let me just write those here. Excuse me. And your Kc is 0.012. So what they did was, if I set up my ice table here very quickly, what I have here is the initial concentration of my HSO4 is 0.5. The initial concentration of water, obviously we're not going to include that because, like I said, that does not get included in your equilibrium expression. The concentration of this guy is 0.020, and the concentration of this guy here, the last one, is 0.060. Now, notice this question here. If you compare this, a quick comparison to the other ones that we did, in the last two examples, you were given the initial concentration of the reactants, and the products were always 0. In this case, they gave you pretty much all of them. So ignoring water, we have one reactant here, and you have two products here, and they gave you all of them. So what do we do in a situation like this? Let's go back and take a quick look at our situation here. So let's say we were looking at this. Here, my initial concentration was 1.5, 3.5, and this was 0. And I put in my negative x and negative 3x and positive 2x here. Well, the negative is always associated with the reactant, because the concentration of the reactant is decreasing. Now, what am I going to do in this situation? Here, I have a reactant, but I also have two other reactants. Now, if you haven't learned, equilibrium can be established either from left to right or from the right. which means it can be established from both directions. That essentially means that I can take HSO4 plus water and it will reach this equilibrium. I can also take SO4 2- and add it to hydronium ion, and that will also reach the exact same equilibrium with the same Kc value. If you don't get that, you can go back and review concepts of equilibrium. So now the question is this: when I'm doing my change line here, do I put a negative X here, or do I put a negative X here? Which of these are my reactants, which are my products? And that's very, very important here. What you need to do now first is you need to calculate the reaction quotient, K. Now, if you recall, the reaction quotient is calculated exactly the same as your equilibrium constant. We use the same expression. So this is my expression here, and here's the concentration of this guy. You're going to plug your numbers in because I don't have a calculator with me right now. You're going to calculate you're going to plug these numbers in and you're going to calculate Q. Let's just say we have a scenario. You run into two scenarios here. Your Q can be smaller than K, or Q can be bigger than K. Now, why are we calculating Q? Well, in this case, I've dumped basically my reactant and these products, or so-called products, at the same time. So what's going to happen is this. The reaction it could be at equilibrium. Chances are the reaction is not going to be at equilibrium. So if my Q is less than K, we have a situation like this. Here's Q and here is K. You should have learned this when you did reaction quotient at equilibrium constant. If my K is bigger than Q, that means that the reaction, if I find the Q to be here, that means that my reaction is not at equilibrium. It needs to go to the right, or it needs to make more products to reach K. If my Q is bigger, let's say we have a situation like this now with K's here, and my Q is bigger here, what needs to happen is that the reaction needs to make more reactants to reach equilibrium. So, very, very important concept here for you to remember. If my reaction is going to go in this direction, in other words, if my Q is smaller than my K, then I will set up my ice table exactly as we did before. This would be negative X, this would not be included, this would be positive X, and this would be positive X. Now, very important for you to know that if we have a situation like this, and I'll put a star beside this because this is the one that's going to give you trouble. If that's the case, then that means my reaction is going to go in this direction. Now, very, very important for you to remember here. What's going to happen now is this side is going to be negative X. Why? Because my reaction is going in the opposite direction. Now, these are considered my reactants and these are considered my products. That only happens if you have this situation. And what's going to happen on this side is this is going to be positive now. Okay? Now, where a lot of kids make mistakes now is once I set up my equilibrium expressions here, equilibrium concentration here. So in this case, if my Q was bigger than my K, which means that my reaction is going left. So these are my reactants now, and this is my product here. At equilibrium, I will have 0.5 plus X, and at equilibrium here, I would have it's a little bit messy here, 0.02 minus X, and this would be 0.06 minus X. When I'm plugging these numbers into my equilibrium expression, now here's the one last thing I want you to remember. When you are writing your expression for this, even though your reaction is going in the opposite direction, based on K and Q, you will write your equilibrium expression for the reaction as it is written. Very, very important for you to know that. What I mean by that is, just because these are my reactants and that's my product now, because of this situation, you do not flip your equilibrium expression. Your equilibrium expression will still look like this. So if I change that to K here, that is my equilibrium expression, and you will write your equilibrium expression exactly the way it appears. So if you go back to these types of problems again, I've told you, if Q is less than K, the reaction goes to the right. Set up your ice table as usual. So in this case, my Q is obviously so here's the number line here. Here's my Q, here's my K. My reaction is going to go to the left. Here, I would set up my ice table just as usual. I would put a negative X for my reactants and positive X for my products. This is the one that you have to be mindful of. If Q is greater than K, we have a situation like this. Here's K and here's Q. Here, the reaction, it's going to be the reverse reaction that's going to go, which means that if I am looking at an equilibrium like this time, this is going to be my reactant and those are going to be my products, which means it's very, very important for you to understand that this is going to get the negative X value when you're doing the change line, and these are going to get the positive. However, keep in mind, in this situation, your Kc is still written for that. Your equilibrium expression is still concentration of C divided by the concentration of A times the concentration of B.